Welcome to this second last lecture in the course. So today would be the last time we talk about new material that might pop up on the exam. So today we will finish off Wi-Fi and then talk a little bit about network security. So last time we talked about Wi-Fi or 802.11, which is the official name of the standards that include Wi-Fi. So these IEEE standards, oops, why is it doing like that? The IEEE standards, they specify MAC and PHY, not the higher layers. And the most common MAC in 802.11 is called DCF, Distributed Coordinating Function, which uses CSMA, carrier sense multiple access, for its multiple access. And you use a variation with the variation called collision avoidance. So the principle for this is like in any CSMA, we listen to the medium before actually trying to transmit. And the medium here needs to be listened over a certain time interval called the DIFS, which stands for a distributed interframe space. And then if it's the medium is idle under this period, then the node can transmit. If the medium is busy, or if something else happens, if we have completed the frame transmission, which includes also receiving an ACK, or if we detect a collision, which is the same thing to say that we transmitted a frame but we didn't get an ACK for that, then we need to do backoffs. Okay. And what is a backoff? A backoff is we wait for a number of time slots. We wait a random number of time slots, and the numbers, the interval that we choose this backoff time counter with randomly is inside something called the contention window. So the contention window is basically the interval in which we draw a random number into. Okay, and the wider this contention window is, it starts at 0 and ends at some number. Or rather, it starts at some number and ends at another number. The lower number is fixed, but the upper number can shift back and forth a little bit. And the reason for this is that we would like to adapt the backoff to the current situation. Because the meaning of the backoff is to randomize the time when stations access the medium. And we want to do that to avoid collisions. But if the contention window is too large, or if it's too long, then we have very few collisions, but we also have long delays. So we always want to make the contention window as small as possible, but not smaller. Which is tricky because we don't know how many nodes are trying to access the medium at any given point in time. So the reason how this is solved in Wi-Fi is that, first of all, what we do, we back off, we count down the backoff counter whenever the medium is idle for a slot time. And this slot time is quite much smaller than the diffs. Okay, so this is some time interval, a few microseconds or so. And if the medium is idle, then we decrement the counter, 5, 4, 3. Okay, and once we reach 0, then we transmit. Okay. So two nodes which has the same backoff counter, they will count 5, 4, 3, 2, 1, 0 and transmit, and they will collide. But if they have different backoff counters, 6, 5, 5, 4, 3, 2, okay, you got it, right? So 1, 0, that means that the one that goes down to 0 transmits, but the other node will notice this and then pause its backoff counter until the frame transmission has been completed, and then resume countdown. Okay. As understood from this procedure here, data frames are always are acknowledged, okay, which means that the receiver transmits an acknowledgement. And the reason for this is that Wi-Fi links are quite unreliable, and we would like to solve any errors locally if we could. So it's sort of like a stop and wait protocol, this. So we use the acknowledgement for stop and wait. So for repeater transmissions, if we get repeater transmissions, that means that we have accessed the medium and there was a collision. We accessed the medium, was another collision. and access to medium is third collision perhaps. And what that means is that it tells us that the contention window we're using is probably too small because it's unable to randomize enough access to the medium. So we want to increase that. So we do the same thing as we do in Ethernet essentially. That is, for each retransmission event, we double the contention window. So if the contention window is this size at the first retransmission, the second retransmission doubles, and the third and so forth, right? So it exponentially grows with the number of retransmissions. And eventually we'll get the frame through, hopefully at least. You know, things could go badly, of course, but at some point we typically get the frame through. This RTS, CTS, we will talk about in a second. Okay, but key to everything that should working in IEEE 802.11 is to use carrier sensing, okay? So how do we do carrier sensing? Well, there are two ways of doing it. One is what we have talked about earlier, which is called physical carrier sensing. And that is basically at the physical layer, we listen to the medium, and then we analyze all the frames that we get in. Okay, so as soon as we listen to the medium, and if we hear something, then we say that the medium is busy. What that means is that we look at the signal strength that we receive, and we measure that, how that varies in time. So if the signal strength is low, then we say, okay, the medium is probably idle. But then if it goes up high for a while, then we say its medium is busy. And then if it goes down to the current, you know, the level it was before, then we say it's idle. Because when you listen to the channel, you will always hear the noise which is on the channel, right? So it's not completely silent. Okay. But we can do something which is smarter, and it will become smarter. We can do this in another way that turns out to be beneficial also, and we can do something called virtual carrier sensing, and that relies on that we detect the frame, and we then actually decode the header of the frame, and in the header of the frame there is some information about telling the length of the transmission, and then we can use that instead of using carrier sensing. Okay, so what do I mean by this? Well, the source stations, that is the station that transmits the frame, informs all other stations of the transmission duration in microseconds for its current frame, including the acknowledgement, the time it takes for the acknowledgements to be generated and retransmitted back. We'll see a timing diagram in a second. But anyways, so the frame header has this duration field that specifies this. And then stations that can decode a frame can have a specific timer. For some reason it's called a network allocation vector. I have no idea why, or a nav field. This timer here can be set to the duration and then just count down until we know that the channel should be idle again. And then we can resume physical carrier sensing. One advantage of this is that we don't have to constantly listen to the channel to do measurements, because we know it's going to be busy for a while. Anyways, the channel is declared busy if either of these methods tells us that the channel is busy. So let's see an example of this. So we have a source which will transmit the frame eventually. We have a destination for which the frame is destined to, and then all other nodes. And we have time on this axis. So the first thing to happen if we want to transmit, if the source wants to transmit, it needs to listen to the medium for this time, the diffs. You know, it's a number of microseconds here, so it's not a small, it's a relatively long time. And that is to be really sure that the medium is free. And also we see that it's crucial that for things to work, that we actually are not, just because the medium is clear here, that we don't go in and transmit. Okay, but anyways, if the medium is declared to be not busy or idle during this period, then the frame can be transmitted from the source. All other nodes that are able to decode this can look into the header of the data frame and figure out the duration field. And the duration field will tell us how many microseconds it is from the start of the frame until we have received the ACK that we expect later on. So it's not only the frame size, but it's also including the ACK that will eventually come here. Okay, and which means that all other nodes that they read this frame, they can say, okay, so there is no need to measure the channel here or here or here, because I know it's going to be busy. So what can the other nodes do during this time? Well, they do as any teenager, they sleep, right? If there is no work, we sleep. Okay. This goes also for people at higher ages, I can tell you. Anyway, so there is no need to work if we can't do anything, right? So we go down to sleep and save energy, battery, right? That's one way to use this. Okay, so just bear with me for a second here. So the next thing that happens is if the destination was able to decode the whole frame here and check for errors and everything, and if everything is okay, it waits from here to here and sends an acknowledgement frame back. And there is some time here, the SIFs, and it's big enough so that the destination can do all the processing it needs to do and assemble the ACK frame and then transmit to start to transmit the frame at this point in time. The SIFs is a short interframe spacing. It's less than a diffs. Okay, it needs to be less than a diffs because if there is a node which didn't hear the nav field that became ready during this time, it needs then to, or it could be even worse, it could be ready exactly at, become ready to transmit the frame exactly at this time, that it starts its period of a diffs in order to measure if the channel is idle or not, and it will, this blue node will think that the channel is idle, right? But then the ACK frame comes, and the blue node can understand that, okay, I'm in the middle of a transaction here. Okay, so if the SIFs was too long, then the blue frame could, the blue user could come in, and then we could cause a collision with the ACK frame. Okay, so the point is that these interframe spacings here are crucial for the protocol, and the shorter the interframe spacing is, the higher the priority the following frame has. Okay, so therefore the SIFs gives acknowledgements priority over data frames. Okay. Okay, so what happens then after this? Well, okay, so somebody who didn't hear the data frame can maybe still hear the ACK frame, and then in the ACK frame there is also duration field, so we can put a nav field for those nodes. So at this point in time, all the nodes that heard the duration fields knows that, okay, now the channel should be idle, or it could potentially be idle at this point in time, and then we wait for a diffs, and then we need to back off, because otherwise there might be many nodes which are ready to transmit at this point in time, and we will cause a collision. So to be safe, in order to avoid collisions, we start to back off at this time. And this is for all other nodes, is for the destination and for the source. Okay, and so we back off for a certain number of frames here. So in this case, maybe it was 4 frames here. Maybe this one got the back off counter 6, which means that these light blue frames here, it will, at this point in time, the back off counter has reached 0. So here maybe there will be a data frame transmitted here. Okay, and that data frame would then be picked up by the source in this point, and therefore these 2 light blue slots will be paused and back off at some later time. Okay, so there will be maybe an acknowledgement here, and then the second node will start to count down its back off slots here, right? And maybe it got successful and then got priority at that point in time. Okay, so we have all these transactions. We have data frames, acknowledgements, nav fields, and then backoffs. Okay. Any questions? Yes.
Yeah, you said that the shorter the zips are, higher the priority the ACK frame gets. How does that work? Isn't it just one ACK frame that it wants to transmit? Can it have more than priority?
No. So the CIF is the same for all ACK frames. So that is no difference. But the thing is that since the CIFs is shorter than the DIFs, it means that ACK frames will have priority of new data frames that got ready to transmit during this time, this idle time. Did that answer your question? Yeah. Okay. So if we would have something which has priority of the ACK frame, I don't know what that should be, then we would have another interframe spacing that would be even shorter than the CIFs. Okay. Okay. So what could possibly go wrong here? Well, many things, right? And the thing is that we have now talked about carrier sensing as being okay. Come on. Carrier sensing being perfect here. That is that all others hear either the data frame or the ACK, or hear the data frame and ACK frame, and therefore do not try to access the medium. So this carrier sensing could actually fail, and we will see a couple of examples of that later on. Another thing that could cause problems is that when suppose both of this one got 4 as a backoff counter and this one 4 as well, then their backoff counter reached 0 at the same time, and then they will also collide. So we cannot guarantee collision-free transmissions here, okay, due to the way the protocol is set up and also due to the physics of the problem. So what do I mean by the physics of the problem? Well, it is like in radio. If we transmit a frame from this laptop to this access point, which is attached here, then the power will quickly decay with distance of this transmission. So if we have a laptop here, C, it might not hear this transmission. So if C makes carrier sensing at the same time as A is transmitting a data frame, it's not guaranteed that C can hear A, because of the power loss over this longer distance than the power loss to the access point. Okay, so carrier sensing, physical carrier sensing in wireless is not perfect. Okay, so what happens now if A transmits a frame and C senses the medium at the same time, because it also has a frame to transmit, but it doesn't hear A. Okay, we say then that A is hidden from C. Okay, so the node A is hidden from C. So what does C do? Well, C thinks that the medium is idle and just transmits a frame, and which collides with the frame from A. Okay. So this hidden terminal problem is essentially that carrier sensing fails, and it fails because a transmission is not heard by all the nodes in the network. Okay, and the frame here could still be decoded here because it has a relatively high power here, but has very low power here. So that it doesn't mean that this frame would never be picked up. It could potentially be picked up by the access point. But here, when we have here a frame coming in like this, a frame coming in like this, then what decides which frame is decodable, if any, depends on the power difference between this frame and this frame. And if they are at basically the same distance, then basically they have the same power, and then they will, most probably destroy each other. Questions? Okay. So this happens, I guess, all the time, right? And that's why we have these retransmission protocols, for one reason. We can actually fix this also, and there is fix this to some degree, or at least to reduce the problem with hidden terminals, and that is to use special control frames called request to send and clear to send, or RTS, CTS. So these are in the standard. However, they're not very often used for reasons that I will explain in a while. So the idea here is that A, who wants to send, before sending transmission, it sends a short packet here, an RTS, which is much shorter than a data frame, to the access point B. Okay. B then answers with this is a request to send with a small data frame called clear to send. Okay. So A asks B, I would like to transmit this, is that okay? And B says, yes it is. Okay. And the purpose of this transmission here, CTS, is that it would reach A, of course it's the intended target, but it will also reach C. Right? Because the distance between B and C is shorter than the distance from A to C. So the CTS will actually be heard by C. And then if C hears a CTS, it can infer that somebody else sends an RTS, and therefore it should keep quiet. Okay. And the reason why this works as opposed to earlier is that these RTS and CTSs are much shorter, so the risk for collisions here, basically that we we send an so the timing of this makes it more preferable to what we had before. Okay, so what happens now is that in stage 2, B has told both A and C that it's okay for A to transmit, and if CTS is heard by both A and B, then C remains quiet. Okay, and then the data frame can go through and the ACK and all these things. So a question on the protocol here? So let's see a timing. Okay, so before going to the timing diagram, there is another problem called the exposed terminal problem. And it looks something like this. So we have 2 access points. And we know we have access points all over the place, right? For the reason to provide coverage. So if station A is attached to access point number 1 and station 2 is attached to access point number 2, then suppose that station A wants to send a data frame. So it's destined to the access point. But then there will be some energy going over to the access point here and some energy going over to the station number 2. Because wireless goes in many directions, not only the desired direction. Okay, so what's going to happen then is that this transmission that goes from station 1 to station 2 will block station 2. When station 2 do a carrier sensing, it will hear this transmission and then back off, right, due to the protocol. However, okay, this one will cause interference to access point number 2, because access point number 2 is not going to try to decode this frame. It's the purpose of access point number 1 to do that. So this would just be interference from the perspective of access point number 2. Okay, now suppose then that station number 2 was permitted to transmit a frame to access point number 2. The situation is symmetrical here, right? So for station 2 there goes a frame to access point number 2. There will be some interference caused to access point number 1, and this one could block station number 1. Okay. Now, if we had this situation, and we forget about the blocking, suppose that the blocking, for the purpose of the discussion, suppose that the blocking was not existing, and these transmissions were ongoing at the same time. Would this be good or bad? Well, it actually depends, right? So what we would like to do is to make sure that the blue frame is decoded and the red frame is decoded. If that could happen, then this collision is not harmful. Okay? And as a matter of fact, then it would be a good situation. The opposite is, of course, if the interference is strong enough to disrupt the decoding of the blue frame here, then it would be bad. That would be a bad collision. But in radio, not all collisions are bad. So as a matter of fact, it's the power of the blue thing to the red thing, the signal to interference ratio, that determines, or actually there will be some noise also here. So the signal to interference and noise power, that is a parameter that typically determines whether access point is able to decode the blue frame or not. But if it's good enough, and it could be good enough, then the blocking of station number 2 was unnecessary. And of course, the symmetrical situation is like this. Okay. So if we have a situation where the SINR is good enough here and good enough here, what we actually would like to do is to make sure that both of these can transmit at the same time. So this is okay. So here, okay, terminology. Station number 2. If it's unnecessarily blocked from transmission, then we say station number 2 is an exposed terminal. Okay, so that's why this is called the exposed terminal problem. And this problem is quite real in real deployment, and that is typically when we have something like this, we have a wall between 2 offices or something like this, and station 1 is attached to access point number 1, station 2 access point number 2, and it's enough power going through this wall to block this, but not enough power to disrupt the frame transmission. So this is a practical problem in real Wi-Fi deployments. Right. Questions? No? Okay. So let's go back in for RTS, CTS, which is fixed to the problem of hidden terminals. So we have, as before, a source, a destination, and some other nodes. Source wants to transmit something. It needs to wait for diffs. And then, instead of sending a frame here, it sends to the RTS. And the RTS is much shorter than a typical frame. The destination, okay, so any other node which hears the RTS will inspect the duration field here and then puts its nav counter to the time it takes to complete the transmission. And complete transmission is the whole transaction, RTS, CTS, frame transmission, and ACK. Okay, so the number of frames that needs to be transmitted here. Okay, the destination waits for a CIFS. We had a question.
Yeah, the lengths of the frames here, are those like predefined here? Can that vary? Do the nav actually adjust to that?
Yes, so the nav would adjust to, when we send a request to send here, we also say, okay, we have a frame of this length that we would like to transmit. And the frame length could vary quite a lot, data frame length. The RTS frame length is fixed. Okay. But anyways, the destination that hears the RTS and is happy with this, waits for a CIFS, and then transmits a CTS. Okay, clear to send. Now, all stations that were able to hear the RTS frame can set its nav to this number. Those stations that did not hear the RTS, okay, and there are some those stations because the source could be hidden to those. Or rather, all the nodes to which the source is hidden will not hear the RTS, and they have no clue on what's going on until they hear the CTS, which hopefully they hear. Okay? Because the CTS comes from the access point, which is in the middle. Okay? The RTS could come from a boundary of the network, and if it comes from this boundary, then the node which is on this side might not hear it. Okay, but anyways, we hope that all nodes either hear the RTS or the CTS, or maybe both. Here both is not a disadvantage. But then all the ones that can hear the CTS frame can put its nav to this number. And then there's another waiting for a CIFS before the source can actually transmit the data frame. And then the poor nodes that didn't hear the RTS or CTS can still look at the data, the frame here to put this nav if they like. And then there's a CIFS, and then there is an ACK, and I guess we put a nav field from the ACK also, if you like. And this completes then the transaction. And let's see if I can avoid killing the slide. Okay, so here we go. Questions on this? Okay. So this is one way to avoid the problems or collisions due to hidden terminals. So what do you, and I said earlier, this is not very often used. Why is that, do you think? Efficiency. Yeah, very good. So this whole thing here, oops. This time here is time invested to avoid a collision that might not have occurred in the first time, right? Because maybe there are no hidden terminals. Right? So actually, in many cases, it turns out, as far as I've been told, I haven't done the experiments myself, is that the overhead here in the RTS-CTS handshake is more than the gain you get by removing the collisions due to hidden terminals. So as far as I know, this is not very often used, but it's not completely useless either. Okay, great. So we have different types of frames, as we've seen. We have the data frames, the acknowledgement frames, but we have a bunch of other management frames. And these are for association, that is to log on to the network or to disassociate, log off the network, for timing and synchronization, for authentication, and so forth. So there's a lot of different other frames that are going through the air in the Wi-Fi system. So we had these control frames that we talked about earlier, the RTS-CTS handshakes and the acknowledgements. And then we have data frames. So if we look at the frame structure here, it follows the same pattern as we've seen before using encapsulation. So we have some payload, and this payload is the MAC layer service data unit. We're in the MAC layer at the moment. And this one comes from the higher layers, which is the LLC layer, as we will see on the next slide. So here we get from 0 to 2,312 bytes. I have no idea why it's not 2,313 bytes, but that's just the way it is, right? Okay, so these could be short and long. And then there is a CRC at the end, which is 4 bytes, 32 bits, which protects everything. In the MAC header, there is a bunch of fields. We had this duration field that we talked about earlier. Okay, we use that to set the nav. There is some control data here that we won't talk about much. And for some reason, there are actually 4 addresses here. I won't talk about why that is the case, but it's just, you know, it's needed for this, sometimes for relaying frames. Then we need a source, a destination, and some intermediate addresses. Okay, it's not super important at this in this course, but it's needed there. And then there are some sequence numbers and things like that. Okay, so the MAC header is 30 bytes in total, and the CRC is using this CCITT32 CRC, and it's over the whole MAC header and the payload. So at the receiver, you can check the CRC. If the CRC doesn't check, then the frame is thrown away. And if it checks, then we send an acknowledgement to the source. Okay, and so this multiple address field is needed for relaying purposes. Okay. If we look at how this looks in the protocol stack, the higher layers to the Wi-Fi MAC layer is the LLC layer. So the payload, the MAC service data unit, is the LLC packet data unit. Okay, just as regular encapsulation. And then when we go down to the physical layer, we go through an intermediate sublayer called the physical layer convergence procedure. All right, it's a long name, but essentially what it does is it takes the bits in this frame and append a physical layer header and a physical layer preamble to that. And these will be different for different physical layers. And so what we have at the bottom here is called a PLCP PDU, right, or a PPDU. I'm not going to ask a question on the exam about this, right? But it's just the way it's called. Okay. And the reason for this layer in between is that there are many, many physical layers in Wi-Fi. Okay, not far from all are used. Some of them are really legacy, they're not used anymore. And the more modern ones are of course heavily used. But this is evolving over time also. So if you remember last time, this was a screenshot from my laptop, and it gave me some data about the Wi-Fi connection I had at the moment. And there were many things, but at the bottom here it says something about transmission rate. It was 59 megabits per second at this particular moment when I took the screenshot. It told me that the physical mode I had was 802.11n. N is a specific amendment to the standard, which is now part of the standard. But when it was considered for the standard, it has these numbers at the end, or letters at the end. Okay, which is a multiple antenna extension to the single antenna Wi-Fi one had before it. And then it uses the MCS index 6. So we'll see what these are in a second. So the actual data which is transmitted on almost all Wi-Fi networks looks something like this. So what do we have here? Well, we have time on this axis, and then we have frequency on this axis, and each little rectangle here represents a time frequency chunk that we can transmit one symbol in, a QAM symbol. Okay. Now, instead of transmitting QAM symbols, one after the other in time, many of them are multiplexed over the entire frequency plane here. Okay, so this from here to here, there's roughly 20 megahertz, and then it's split down into how many? It's 52 subcarriers, I believe. So each of these frequencies here are called a subcarrier. So if somebody can count these and figure out how many, I think there are 50. Well, actually, it's 26 plus 26. Which is 52. Yeah. The ones that are in white are not used at all. Those who are in blue are for control purposes. So this is the physical layer preamble, these blue parts. The yellow parts here is the physical layer. So the preamble are the first blue parts. And then the yellow thing is the PLCP header. It goes here. And actually there are 16 bits which are carried around in the green part here also. And the green part here carries all the payload and the CRC bits. Okay. The first part here, this yellow thing here, is using 2PAM or 2QAM or BPSK, same thing. So it's BPSK 2QAM modulation with a very strong code on it. And that's the reason these bits are heavily protected. And then the green part here can go in many different types of QAM depending on what transfer rate we have, basically what signal to noise ratio we have. Okay. Questions? Yes.
Do you know if the digital TV uses waveform?
So how does digital TV fit into this picture? Well, it uses this OFDM, as is known, orthogonal frequency division. So they have these type of subcarriers and things like that, but with completely different parameters, length and spacings and so forth. But OFDM is a very popular physical layer nowadays. It's used by LTE, it's used by Wi-Fi, it's used by digital broadcasting, both for video and for audio. And a variation of this is used also for these ADSL telephone modems that we used to have before we had fiber. Okay, so it's very, very popular physical layer now.
You mentioned on a previous lecture that the physical layer with the Wi-Fi standard has some sort of error correction function, is that built into the preamble, or where is that coming?
I'll show that on the next slide here, I think. But basically, it's we have for error detection, we have the CRC here. But then we also protect these bits with the error correcting code, which is used by the receiver to correct as many errors as possible. But when it's pushed up to the MAC layer, then we look at the CRC to detect any remaining errors. Okay, so we have the error correcting code operating on these bits in order to clean up as much as possible. Okay, and which one we use depends. We have many different types of physical layers, but if one looks in the standard, there is a table like this, and we have different modulation formats here. 64 QAM is the highest one, so 64 one carries 6 bits per symbol. But then we can also use a binary one which carries just 1 bit per symbol. And then here is the coding rate, and essentially what we can say here is that the lower the coding rate is, the more powerful error correction we are employing. So this is 1/2 is the lowest coding rate here, so it's the most powerful error correction code. So this one we use when we have channels which are bad. If the channels are better, then we can use a higher coding rate and we get more bits. We have a higher bit rate, essentially. So 3/4 is the highest here. We can also use 2/3. And all of these are using, it's called a convolutional code. It's not super important in this class, this course. Okay, so we do error correction on the physical layer, error detection on the MAC layer, and retransmissions on the MAC layer. Okay, yeah. Okay, but I promised you to say something about the modulation coding index here, and in the screenshot I used number 6, which means that it used the 64 QAM with 3/4 convolutional code, rate 3/4 convolutional code. There's a bunch of other stuff here, but then it says here that we had a data rate of 59 megabits per second, which seems to be consistent with this table. Now, if I was in a situation which was a little bit worse, maybe that I was further away from the access point, I would probably choose a lower modulation encoding index, and then I get a lower data rate. Okay, but if I don't do that, I will get 0 data rate, because if we transmit with too high of a signal constellation here, you know that the error probability will be very high when the signal to noise ratio reduces. Okay, so we go back up and down here, depending on the situation. Right? So this is reconfigured automatically, no user interaction really. Questions? No? And you know also that today we have Wi-Fi's where you can do close to or exceeding a gigabit per second also. And these use multiple antenna technology, both at the transmitter and receiver, and many other tricks to get this to go, to work. Right? And there's a constant evolution of this. Right? Questions? No? So then that drops Wi-Fi and everything like this. So the final part of the course. Question?
I actually have a final one.
Yeah.
With Wi-Fi, then you said that some of them uses multiple antennas. Do they actually use different frequency bands? So
For the different antennas?
Yes.
No. So the key thing is with if we have 2 antennas here, 2 transmit antennas and 2 receive antennas like this. If we look at the number of paths between the antennas here, there's one like this and one like this, right? And there is maybe one going like this and one going like that. So whatever transmission we do here will interfere with the green one up here, and vice versa. So this creates collisions and interference. But with a little bit of magical signal processing, we can process the received signals so that we get these virtual channels like this. Okay, interference-free channels. And this is done by processing the real received signals and canceling out this interference. And then we get two channels, interference-free channels, that are operating at the same time in the same frequency bands. We double the capacity by doing this. Okay. And the cool thing is that if we add a third antenna like this, then at least in theory, we get a third channel, and a fourth, and a fifth, and a sixth. Okay. Of course, there are some limitations that I brushed under the rug right now. But in 5G, one talks about something called, this is called, by the way, this is called MIMO, multiple input, multiple output. And in 5G, one talks about massive MIMO, where we can have maybe 100 antennas like this. Okay. And that's a super hot topic right now, and it's super complicated to make it work, right? Because it's a very difficult engineering problem to get it to work. But we're working on that here, for instance, right? As any other place in the world, I think. But it's cool. And this MIMO technology is really the driver for high data rates. Without that, we would still be stuck at 20 megabits per second or some 40 megabits in these type of channels. Okay. Anything else? Let's take a break.